betas or f betas. Okay, so it has to be something like maybe n cubed times 1 over epsilon to the 100. This is allowed, but what I showed you earlier is not allowed. Because you now need to be polynomial in both n and 1 over epsilon. The dependence on 1 over epsilon cannot be crazy. Okay? Any questions about the definitions? Good. So in fact, problems are usually categorized. NP-hard problems are usually separated into two categories: problems which admit f-betases and problems which do not admit f-betases. Somehow we feel that f-betas is almost like a polynomial time algorithm. It's not quite. These are NP-hard problems, but they're very close to polynomial time. Problems which do not admit f-betases, which do not have f-betases, are quite far from polynomial time algorithms. Okay? So to capture this, we call these problems that have an f-betas, we call them weakly NP-hard, and problems which do not have an f-betas, we call them strongly NP-hard. Okay? So a problem is weakly NP-hard if it has an f-betas. Now it turns out that the question of whether a problem has an f-betas or not is very closely related to the question of whether the problem has a pseudo-polynomial algorithm. Okay? So you have seen there are three categories of algorithms. There are strongly polynomial algorithms, there are weakly polynomial algorithms, and for both strongly and weakly polynomial algorithms are polynomial in the sense of the complexity class P. And then there are pseudo-polynomial algorithms, and we kept saying that pseudo-polynomial is not really polynomial, but we still say it's pseudo-polynomial. Now this is why we still consider it to be almost polynomial. Because if you have a pseudo-polynomial algorithm for the problem, then you can convert it into an f-betas, and if it has an f-betas, then it's weakly NP-hard, it's not strongly NP-hard. Okay? So what's the problem where we saw a pseudo-polynomial algorithm? There was one problem that we studied earlier where we saw a pseudo-polynomial algorithm, but we haven't seen a polynomial algorithm.
We then tried to increment, right?
Sorry?
You then brought up incrementing by a larger value.
Increments by. So we
just
saw
scaling algorithms.
We saw two pseudo-polynomial algorithms, right? One was for max flow,
Yeah.
but max flow does have polynomial algorithms, real polynomial algorithms. We just didn't see it in class. But there was another problem for which I gave you a pseudo-polynomial algorithm, and this problem in fact is NP-hard. You cannot have polynomial algorithms. So this was the 0-1 knapsack problem. Okay. So again, let me remind you of the problem. So you have a bunch of items. Okay, let me call them A1 through AN. You have a knapsack of size B, and each item has a size and a value, also called a problem. And the goal is to find a subset of items of an S such that the total size of the items is at most the capacity of the knapsack B, and the total profit of these items, or the total value of these items, is maximized. Okay? So again, you have a knapsack, there are a bunch of items, the items have a value and a size, and you want to maximize your value or the profit while ensuring that the items that you pick actually fit in the knapsack. So the sum of sizes is at most p. Okay. So for this problem, we saw a pseudo-polynomial algorithm. And anybody remembers how this algorithm worked, even at a very high level? This was a dynamic program, one of the dynamic programs we saw in class. Okay, so let's go back to this dynamic program. See how this algorithm works. So there are multiple ways that the dynamic program for this problem can be written. I'll do it in a particular way that will help me in converting it to a FP task later. So imagine that in your dynamic programming table you have two dimensions. So one dimension gives you the items. This is item 1, 2, so on through item n. Okay. The other dimension gives you the value of the profit. So these are the items. This is the total profit. Firstly, if P is the maximum profit among all the items, then what is the maximum profit that the knapsack can hold? What is a very rough upper bound on the total profit of the knapsack? If I have n items, P is the maximum profit of an item, then clearly the knapsack cannot hold more than an NP profit, right? I mean, in the best case, I'll take all the items, and then even then my profit would be smaller than NP. So clearly I can't do better than NP, so this is my dynamic programming table. Now what does every cell represent here? So let's go to a particular cell. Okay? So let's say this is the cell AIP. Okay? So this will represent the minimum weight carefully. So this will represent the minimum weight of or minimum total size of set of items having total profit exactly equal to P among the items A1 through AI. So I'll look at the first I items. I order the items arbitrarily. Look at the first I items. And what this represents, this cell will represent, is the minimum total size of some subset selected from these items, such that the total profit of this subset is actually exactly equal to P. Okay, so this is the semantics of every cell in my dynamic programming. So firstly, forget about being able to compute this. If I were able to compute this, why can I solve the knapsack problem? Which cell gives me the answer? Yeah.
The cell with the biggest P, such that I equals n.
Okay, so firstly you go to I equals n. Now you go to the cell with the biggest P, this is the cell. But the minimum weight of total size of these items might be larger than P, right? And therefore may not be feasible. So I need to start here and I need to start walking back along this row till I hit a cell where the value is less than P. Okay? Whichever cell I hit, the corresponding column will give me the answer. That's the maximum profit I can make. Okay, this is not particularly important for this, for how we do the transformation, but this is something for you to understand. That is why this dynamic program is sufficient. If I am able to construct this table, then that's sufficient. I can find my answer. Now, how do I find this table? Can you write a recursive relation for ai plus 1p? And let me also give you two cases. Case 1 is the I plus first element item has profit greater than p, and case 2 is this guy has profit less than p. So what happens in case 1? If the I plus first guy has profit greater than p, can that be included in my set? No, right? Because my profit needs to be exactly p. So the I plus first guy cannot be included, which means that what should this entry be?
A of IP.
Exactly. This entry should be just A of IP. Right? Because the I plus first guy cannot be included, so the question really goes back to what can I do with the first IL items? What if this can be included? Then what are my choices? Again, let me tell you that there are two possibilities. So it's minimum between two things.
You have a of I minus 1 and then p minus p of I plus 1.
Right. So firstly, what are these two things? So either the I plus first item is included or it's not included. Okay? If it's not included, then what is my solution?
A of IP.
A of IP. So this is the case where I do not take the I plus first guy. In this case, I could not take it. So there's only one case. Here, I might be able to take the I plus first guy. It depends on whether that gives me a smaller total weight. So this is one of the options, to just ignore the I plus first item. The other option is to take it. So if you take it, then what you were saying holds. So what is the expression then? I take the I plus first guy. Okay?
So you have to find the a of I minus 1, p minus p of I plus 1.
So A of I, P minus Pi plus 1. I have taken the I plus first guy. So now I have to fill up the remaining profit using the first I guys. Okay? So this is this. But then I also have the size of the I plus first guy. I've already picked it. So this plus Si plus 1. Right? Is it clear? So in one case I have AIP, in the other case I have the sum of these two things. I already picked the I plus first guy, and now I am trying to fill up a profit of P minus Pi plus 1 in the best way I can from the first I guys. Is this dynamic program clear? Good. So what is the running time of this algorithm? How much time do I need to fill each cell? O of 1. All I'm doing is I'm reading cells I've already filled up, right? And doing some arithmetic. So it's just O of 1. And how many cells do I have?
N squared.
NP times N, right? So the total time I take is N squared times P. Why is this pseudo polynomial and not polynomial? Because of P, right? P is a numeric input. As I have kept telling you, if you have a numeric input, it's a number, right? The maximum profit is a number. P is, it's not that the input consists of P different things. P is a number, it's the maximum profit. So this is polynomial in this number, and therefore this is not a polynomial time algorithm. Okay, it's a pseudo polynomial. But how can we make this polynomial? Maybe there's a clean way of making this polynomial by using an approximation factor. So the trick will be something that we use a lot in algorithms, which is to use scaling. Okay? And what is scaling? Basically what we will say is that, look, the reason we were taking so much time is because there were all these various values of profits that we had to consider. Yeah.
Are scaling and heuristics kind of the same thing?
Sorry?
Scaling and heuristics?
Scaling and?
Heuristics, like HEU.
Heuristics? So heuristics are a more general term. Heuristics mean anything that is not an optimal algorithm. Okay? Scaling is a technique, it's not a class of algorithms. So the idea of scaling is to say that, look, the reason I was in trouble is because I had to consider all these different values of profits. So somehow I'll restrict the number of values of profits that I consider to some fairly small set. Okay? And the way I do this is the following. I first select k. This is my scaling parameter. I select it to epsilon. Remember, there's an epsilon given to me. I'm trying to get an algorithm which runs in time, polynomial in 1 over epsilon and n, and gets you a solution whose value is at least 1 minus epsilon times opt. This is a maximization problem. So the value of the algorithmic solution should be at least 1 minus epsilon times opt. Epsilon is arbitrary but fixed. It's given to you. So what you do is you start with the scaling parameter epsilon p over n. Okay, and you'll see why this is the right scaling parameter. Your next step is to take every profit and replace it with something that's scaled. Okay? So I take every profit value, I scale it by this number k, and then I round it. I just take the flow. This is my new profit. And the third step is simple. I run the DP. So I just run that algorithm now on the instance wherein I have replaced profits with P star with this value. Okay? I simply run it on this modified instance where profits have been replaced by P star. So even before we analyze the approximation ratio, what is the running time of the algorithm now? So as we saw, it's n squared times the maximum profit. What is the maximum profit in terms of P squared? Sorry, in terms of P star. The maximum profit earlier was capital P, okay? I have scaled it by k. Yeah.
The,
So I've scaled the capital P by k, right?
Over epsilon?
Right. So the maximum profit now is P divided by k. Right? I've scaled it by k. So P divided by k, the way I've chosen k is that P divided by k is just n over epsilon. So running time of my algorithm is now n squared times n over epsilon. My maximum profit is much smaller. Okay? And this is in fact a p-task. Right? As I said, a p-task will need to be polynomial in 1 over epsilon and polynomial in n. And that's what this algorithm is. So the only question is, if I do this, how much of an approximation factor do I get? Clearly, this is not an optimal algorithm. It's not solving the problem on the original instance, so it's not solving it optimally. But how bad is it? Okay? So that's what we will try to analyze. So first observation is, if I thought of the transformed instance as the original instance, so what is the transformed instance? I've taken all the profits and replaced them by P star. So if this were my original instance, then what is my algorithm getting me? Is my algorithm optimal then? It is, right? Just simply follows from the fact that this dynamic program is optimal. So if my transformed instance was in fact P star, on this instance with P star, my algorithm in fact finds an optimal solution. So this is my first observation. So the algo in fact finds an optimal solution where prices have been, profits have been replaced by P star. Okay, just from the optimality of the dynamic program. So all we need to do is to compare the optimal solution for P star and the optimal solution for P. Okay? So in fact, the first thing is so P star has a scaling of K. Okay? So the final solution that we report will scale it back up by K. So you run the DP on P star and S, scale all profits by K. Okay? So this is without loss, right? Because I have scaled it down by K, I can scale it back up by K. Okay, this rounding is the thing that will lose some factor for me. If I did not do the rounding, if I didn't care about round, why did I round? This is the first question to answer, right? So if I did not do rounding, then well, I could have scaled it down. My maximum value of profit would have still been n over epsilon, and I would have run this algorithm in this amount of time, and then I could have scaled all the profits back up by K, right? I am scaling down by K, later I can scale up by K, I get the original value. So why was it crucial that I rounded here? If I did not round, it seems I would have gotten an optimal algorithm. Yeah?
The rounding is what makes like a smaller set of discrete values of profit, and that's what allows you to run it faster.
Exactly. So in this dynamic program, I'm assuming that all the profits are integral. Right? If the profits weren't integral, I couldn't have run this dynamic program. And this rounding allows me to run the dynamic program. Because if I didn't round, there's no guarantee that my profits would be integral. And if the profits are not integers, this dynamic program is not valid anymore. Right? Because this is assuming that your profit, the final value of profit you get is an integer. So therefore it's crucial that I did this rounding, that I did this, I took the floor of Pi over T. Okay? If I did not take this, then I wouldn't be able to round the dynamic program. And this is where I'll get a loss. This is where my algorithm will not be optimal. So let's try to analyze the distinction. So let's actually make this K times, because there's a scaling factor of K. So what we really need to do is we need to compare K times opt P star versus opt P. Okay, we need to compare these two things. How do we compare? So let's take the optimal solution for P. What is the value? If I took the same solution, remember my sizes I haven't done anything to the sizes. The sizes remain exactly as they were. So any feasible solution with prices with profits equal to P is also feasible with any other profits. Feasibility only depends on sizes, right? The items must fit in my bag, in my knapsack. So any feasible solution remains feasible. In particular, the optimal solution, opt P, this solution, how much value does it give once I do the rounding? What is the profit of this solution after I have scaled and rounded? How much do I lose? How much profit do I lose in the rounding? So I have a particular, let's say a particular item is giving me profit Pi. I go from Pi to Pi over K floor times k. What is the difference between these two? How large can this difference be? At most k, right? So I know that Pi is at most this plus k, right? But what is this? This is simply P star I times k plus k. Okay? So what that means is that opt of Pi or opt of P is at most k times opt of P star plus k times the number of elements you have, k times n. Right? Again, Pi is at most Pi star times k plus k. Now, this additive terms, there are at most n elements, n items in your knapsack in the optimal solution. So the additive terms add up to at most n times k. So the difference between opt P and k times opt P star is at most n times k. Okay? So this is the comparison I have now been able to do between the two things. But that's not good enough yet, because what I finally want, and of course algo is simply this, right? So algo is simply equal to k times opt of P star. And we have shown that that's at least opt of P, the original opt, minus nk. Okay? So how do we now write, so but this nk is a problem, right? Because I wanted to say that this is in fact 1 minus epsilon times opt. So what should I now do? I just replace k, right? K is the parameter I chose myself. So I just say that algo is, I've already shown that it's at least opt P minus nk, but k is something I chose. K is epsilon capital P over n. Okay, this is just my choice of k. So this is opt P minus epsilon times capital P. But of course, opt is at least as large as the largest profit, right? Because I can take just the biggest, item with the largest profit and place it in the knapsack. That's the only item I have, right? That's always one solution I can compare against. So opt is at least P. So we can say this is at least opt P minus epsilon times opt P, which is 1 minus epsilon times opt, which is what I wanted. Okay, so this is an example of a problem of an algorithm which runs in time polynomial in 1 over epsilon and in n, and gives you a solution that's at least 1 minus epsilon times the optimal solution. And note that in this entire story, epsilon is completely arbitrary. I can start with epsilon equals to 1 over a billion, and this will still work. Okay, it's just that you will have this, the billion will show up in this running time. All right. By the way, so I just want to mention that I'll be traveling next week from Wednesday through Friday. So if you guys have any questions, I won't be there for Thursday office hours. So if you guys have any questions, you should come on Tuesday.